The proof is very simple. We just use triangular inequality, and we say that the distance between u and that set A is less than d of u and v plus d and v and A. And we can say that fi of u minus fi of v is du and ai minus dv and ai. This is less than du and v. Proof is complete. So we can say that isometric embedding into L infinity that I described is a Freche embedding. And I want to talk about clustering because I want to talk about padded decomposition. But what is a good clustering? The desired properties of that is that we want small diameter, we want connectivity, we need nearby vertices are likely to be clustered together. So nearby vertices are likely to be clustered together. So these are the properties that are desired. So in padded decomposition, we have distribution over partitions. So we say that distribution over partitions of G is beta and delta padded decomposition if for every cluster C inside P, and the P is drawn from the distribution D, is delta bounded, and every small z in V, the probability BG, the ball of center Z and radius gamma delta, is inside the partition that belongs to the Z. If this holds, then this probability is greater than equal to minus beta gamma. So recall from locality sensitive hashing that we make random partitioning by sampling from Gaussian vector and make inner product and etc. And all of them are now can be seen as a random partitioning. So embedding embeds different clusters and we glue it together. So the idea is that. And we glue it together so that the distances are preserved. Okay, so that should be proved. So let me talk about strong and weak diameter. A weak diameter is the weak diameter is different from strong diameter of A, and it is the maximum of V and U for any U and V in V. But the strong diameter of A is maximum of the G. This is the induced subgraph V and U. For example, let me give you the example that Arnold uses in his lectures. And because I don't have creativity, I just use the example of Arnold. Also, its examples are very easy and interesting. And so let's see this one. As you see, the distance between U and V is just 2. And distance between U and V is 6. So the strong diameter of A is 6, but the weak diameter is just 4. And he proved in a theorem that sparse net implies padded decomposition. So if we have a graph V and E, it is weighted and delta is greater than 0. And suppose there exists set N, these are a set of centers, which is inside V of centers such that for any V in V, we have covering. It means that there exists T in N such that dg V and T is less than delta, and also packing. It means that the distance, the ball of center V and distance and the radius 3 delta, intersection of that with the subset of centers is less than tau. The cardinality of this set, this is the cardinality, is less than tau. And for example, these are some centers, and then this is delta radius, and then we have 3 delta radius. So G admits a strongly padded decomposition. G admits strongly padded decomposition. So he has proved that by construction. So one nice embedding that you can think about it is so I will talk about these after my publications, but let's see a method to create random partitions. Random partitions. So let N be a subset of V, be some set of centers such that for any V, dg of V and N is less than delta. And then we sample delta x in delta using truncated exponential distribution. Each vertex will join cluster Cx of the center x in N, for which the value of delta x minus dg x and v is maximized. In other words, you are minimizing this one and maximizing this. So maximize this one is equivalent to that. And so each center x wakes up at time minus delta x and begins to spread in a continuous manner. And this is the idea of ball carving. That first I need to say what is ball carving. So we iteratively create clusters by taking a ball centered around some vertex with radius drawn according to that exponential distribution that I talked. And the process halts when all the vertices are clustered. Intuitively, if every vertex might join the cluster associated with at most tau centers, the padding diameter is order of log tau. We can think of these centers as threateners. The current algo that Arnold uses in his algorithm is a variation of the algorithm of that guy in MIT. I forgot his name. So each center samples a starting time delta x. Samples a starting time delta x. So vertex V joins the cluster of center xi maximizing delta x minus the x and v. And this approach guaranteed to create strong diameter clusters. And the key observation is that for every center y, which is not xi, the interesting things that I'd like is that delta xi minus dg xi and v minus delta y minus dg y and v, this is greater than 2 gamma delta. For every center, if this holds, then the both b, g, v, and gamma delta is fully contained in the cluster of xi. Using the truncated exponential distribution, we lower bound the probability of this event by e to the minus gamma order of log tau, where tau is the number of centers. So, theta 1, theta 2 truncated exponential distribution with parameter lambda is like this: f of y lambda e to the minus lambda y over e to the lambda e to the minus lambda theta 2. And in his article, lambda is 2 plus 2 ln tau, and delta is inside 0 and delta. And so I want to claim Arnold proves this interesting claim. Every non-empty cluster Cx created by the algorithm has a strong diameter at most 4 delta. The proof is very simple. We consider V in C of x. First, we argue that V and x is less than 2 delta, and xv be let xv be the closest center to V. Then dg of V and xv is less than delta. So as V join the cluster of x, it holds that delta x minus dg V and x is greater or equal to delta xv minus dv and xv. And in particular, we can say that dg v and x is less than delta x. This is less than delta, plus dg v and xv, and this is less than delta. So overall, it's less than 2 delta. Let I be the shortest path in G from V to X. For every U in I and center X prime in N, it holds that delta X minus d of U and X is delta X minus dg V and X minus dg V and U greater than equal to delta X prime minus dg V and X prime plus dg V and U. This is greater than equal to delta X prime minus dg U and X prime. So we conclude that I is a subset of Cx, in particular that dg of Cx of V and X is less than 2 delta. And this dg V and X less than 2 delta implies that Cx has weak diameter 4 delta. So this is the first claim that you need for the proof of the main theorem of Arnold. The second important claim that Arnold proves is that consider vertex V and let x1 through xn be an ordering of centers such that with respect to delta x minus dv and x, such that the delta x, so we are just sorting them because the algorithm by construction creates something like this. So I just want to sort them. And the gamma is defined by delta x1 minus the Vn x1 minus, so the top two biggest differences, Vn x2. So this is by, everything is calculated by just triangularity. So I just use a triangular inequality. So if this holds, then for every vertex u, d of v and u is less than gamma over 2, it holds that u is in Cx. And the proof is just one line, that for every center xi not x1, it holds that delta x1 minus d of u and x1 greater than delta x1 minus d v and x1 minus gamma 2, and this is greater or equal to delta xi minus dv and xi plus, using ordering of delta xi minus vi, I use this, and this is greater than delta xi minus the u and xi, and in particular, u is in Cx1. And now we are ready to use claim 1, claim 2, claim 3 to prove the main theorem. So the proof of main theorem that Arnold has proved is, he showed that by claim 1 we can create a distribution over a strongly 4 delta bounded partition, and we will argue that the ball B equal to BG V and gamma delta, where gamma is 1 over 4, is fully contained in P of V, with probability at least e to the gamma log tau. And following the calculation in claim 1, each vertex joins the cluster of a center at distance at most 2 delta. So by triangular inequality, all the centers in N are at distance at most 2 plus gamma delta, which is less than 3 delta from V, and in particular NV, the cardinality is less than 2. So we set NV to be x1, x2, the ordered, but arbitrarily, and we denote by Fi the event that V joins the cluster of X, where V is in Cxi, and we denote by this event the event that V joins the cluster, but not all of the vertices in B join that cluster. That is, V is in Cxi intersection of B, but it is not all B. So to prove the theorem, it is enough to prove that the probability of union of Ci's is less than 1 e to the minus order of gamma lambda, and we set alpha is equal to minus 2 gamma lambda, and so this is proved. But because of the interesting thing in claim 3, I should mention that in claim 3, for every I, probability of Ci is less than equal to 1 minus alpha probability of Fi plus 1 over e to the lambda minus 1. And we bound the probability that the ball B is cut, so the probability of union of Ci's, I will prove this later, but I just want to continue with the proof that the probability of intersection, probability of these events, is less than equal to 1 minus alpha I from 1 to NV probability of fi plus 1 over e